तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last few lectures, we have been seeing about combinational logic. In particular, we took combinational logic which could be implemented using off the shelf devices such as multiplexers and decoders. Now, very few systems, digital systems, very few digital circuits or digital systems are purely combinational. Most of the circuits and systems in digital are combination of combinational and sequential, but in our case it is a combination of combinational and sequential. Whenever there is a sequential element involved, you call it a sequential circuit, even though there will be a combinational logic part of it. Let me not go into the details of the combinational sequential logic differences and all that, which you would have seen in your first course. I can only say that no system can be designed without a sequential block, no practical system. Let me say, no practical system can be designed without sequential elements. And so, in this first lecture on the sequential circuits, I am going to introduce you to the building blocks which are already familiar to you, just as a review. All of you know that the most elementary building block of a sequential circuit is a latch. It is called SR latch or RS latch, depending on how you name it. It is two NOR gates connected back to back. You also have an equivalent version using two NAND gates connected back to back. Now, this table all of you must be familiar with. The inputs are called R and S, meaning reset and set. When you put a 1 in the reset, the output Q becomes 0. When you put a 1 in the set S, the output becomes 1, and when you remove the inputs R and S and make them 0 0, output will remain what it was earlier. That is, if you want to make the output Q 1 and Q bar 0, of course, Q and Q bar are always complementary, you make S is equal to 1, R is equal to 0. That means you set the flip flop by making S is equal to 1, R is equal to 0, set the latch, and then that makes Q is equal to 1 and Q bar is equal to 0. If you want to put a 0 at the output Q, it is called resetting operation. You put a 1 in R, the reset input, and a 0 in the set input, then this becomes 0 and this becomes 1 automatically. And either way, whether it is a 1 0 or a 0 1, when the input is removed, that means when you make the input 0 0, either after 0 1 input or 1 after 1 0 1 input or 1 0 input, the output remains what it was before removing that input. That state is called memory state, also called Qn. So, we are now talking of before setting and resetting, if the output was Qn, after applying 0 0, this will still remain Qn. That is what it means by Qn plus 1. This state is also called memory state. That is the basic feature or the characteristic of a sequential circuit, a memory unit. This is the reset operation, as I said. This is the reset, this is the set operation, this is reset, and 1 1 is not applied because after 1 1 input, when you give one of these 3 other inputs, the output is not determined. The output will be determined based on which of these 2 gates is faster. Since we do not have that information, also because we do not want this unreliability to be built into the circuit, we never apply 1 1 as an input to the RS latch. This RS latch. Now, this any latch, you need to keep the, when the input changes, the output changes, but we would like to have the input changes in the output controlled by another event called the clock. So, when you have a clocked latch, you introduce a extra input in addition to S and R, set and reset inputs. This is RS latch. Or SR latch, whatever. When you have a clocked RS latch, you introduce an extra input called clock input. The function of the clocked input is to make sure that the changes in the output occur only when the clock is active or high. The inputs may change, output will not change if the clock is low. Output will change when the input changes only if the clock is high. Such a latch is called a clocked latch, also called a flip flop. So, what do you do? You put an extra gate at the input to control the clocking. So, this is my R, S inputs, both of them are controlled by an AND gate whose another input, the second input is a clock, that is all. If you put an AND gate with an extra input connected to the clock, naturally the output will R or S will pass through this gate only if clock is 1. When the clock is 0, output will remain 0. You know that. In AND gate, 2 inputs, one of the inputs 0, the output is always 0, which means whenever the clock is 0, this is 0 0 and 0 0 corresponds to memory state, no change in the output. No change in the output because inputs are 0 0 and input are 0 0 does not make any change in the output. On the other hand, when the clock is 1, whatever is there in R, it will get passed through this gate, whatever is S will get passed through this gate, and then the circuit operation will be determined by the either a 0 1 or a 1 0 combination as we wanted. So, in this case this will be the additional you want to call it Qn plus 1, so they will call it Qn, n is suffix saying the nth input and n plus 1 is the next input. So, with the clocked operation, there are 3 inputs and 2 outputs for this flip flop or a latch, clocked latch or a flip flop. Now, a modification of this flip flop is a D flip flop. Since we are only interested in either setting or resetting the flip flop and keeping it there, we can do away with one of the inputs. For example, if we want to put a 0 in the output of the flip flop, we need to make R is equal to 1, S is equal to 0 and make clock high. Then the output becomes Qn is equal to 0, Qn and Qn bar is 1. And when you remove the clock, output remains 0. Likewise, if you want to give a 1 1, I mean you want to give a store a 1 in the flip flop, you make S is equal to 1, R is equal to 0, clock it, output changes to 1, remove the clock, output continues to be 1. Now, instead of making, in order to make a 1, I need to put a 1 here and a 0 here. In order to get a 0, I will put a 1 here and a 0 here. 2 inputs need not be done, it is always complementary. So, why do not we do away with one of the inputs and have only one input? That is called a D latch or a D flip flop. We will call it D flip flop because once we have already introduced the clock concept, we can continue to call all the other circuits as flip flops. I will always, we will always have to mark a clock input. So, this clock flip flop would be same as the clock SR flip flop, with R and S inverter of each other. So, this input is called a D input. A D input, if D is 1, D bar is, this is, so if this is 1, this is 0, you get a Q is equal to this one, this is 0, Qn will be 0. This is 1, this is 0, Qn will be 1. This is a D latch. So, you don't want to show all this extra gates. You put a D here, SR, oh okay. I think I made a little, it is not a mistake, actually a little out of the convention. I will tell you what it is. You go back to this RS latch with a clock which is called RS flip flop. R is 1, S is 0, output is 0. R is 0, S is 1, output is 1. But then when you want to have a, this is a clocked latch. Now, when you want to have a 1 stored, you would like to have a 1 here. Now, according to our, by just connecting this inputs through an inverter, when this is 1, this becomes 0, that means I will have a 0 stored here. When this becomes 0, this becomes 1 and 1 gets stored. So, I will store what is the complement of what I give as the input. I will store, so it is really not a D latch in the sense D gets through R and output is, if 0, output is 1, if R is 1, output is 0. We do not like to call it a D latch, so strictly speaking we want to call it a D latch, D bar. How can we solve that problem? By putting an inverter at the input here, that is, instead of changing this AND gate into a NAND gate, if I change this AND gate into a NAND gate, what will happen is this R and S roles get reversed. So, then if I put a inverter here, so now I am going to do this. I am going to leave this circuit alone because I do not want to make too many changes in the original circuit, leave it alone. Just I want to show you what will happen. I am going to leave this circuit alone where you had in your notes. I am going to make the change here. I am going to call this S, I am going to call this R, which means when D is 1, Q is 1, when D is 0, Q is 0. That will be more like match data storing. A 0 is stored, or a 1 is stored. If you want to store a 1, put a 1 here, clock it, 1 gets stored. Remove the clock, 1 continues to get stored, continue to be remaining there. Similarly, you want to store a 0, put a 0 and clock it, 0 gets stored, remove the clock, 0 continues to reside inside. So, this is the D flip flop. What we have got earlier with an inverter of the simple RS flip flop would have been a D bar flip flop. We do not want a D bar flip flop, normally it is not used. That is why I said it is not a mistake, it is a convention. In textbooks you will find D flip flops, not D bar flip flops. That is why I thought I will change myself and call this S and R. That means an S and R flip flop would be different from this flip flop, RS flip flop, where AND gate will be changed into a NAND gate. So, this SR flip flop what I have in mind here is this. This will be my S R clock, and then my 2 So, this is an SR flip flop, and now if you make this S and R invert of each other, I call it a D, this is a clocked D flip flop. We are also familiar with the next flip flop called JK flip flop. See, the problem with the SR flip flop is if one of the conditions, in this case an RS flip flop 1 1 or SR flip flop whatever, 1 1 condition is not allowed, because that I said leads to the undefined operation afterwards. 1 1 will not make, 1 1 is not a problem. First of all, 1 1 will not give you a complementary output. Q and Q bar should be complementary in a flip flop. That will not happen if you put 1 1. Second problem is, once you put a 1 1, when you remove 1 1 and put some other input, the operation is not defined. The operation is defined based on which of the 2 gates is faster, which I do not want. I do not want an unreliable operation for my flip flop. Now, because of these things, we want to remove this possibility of this 1 1. Always remember not to give this input if something is a restriction, constraint, which a circuit designer does not want. So, you want to put that some operation for this 1 1. That is why a JK flip flop came about. We will see how it is done. Before that, we will see how a JK flip flop is connected. Now, take this flip flop, the SR flip flop with a NAND input, take that, and Q n bar or Q bar, does not matter. This is my S R clock. What I am going to do is to take the output of this Q n and connect it to this input, Q n bar, and connect it to this input, and take Q n and connect it to this input. That means I am making these 2 input NAND gates as 3 input NAND gates with an extra input derived from the feedback of the output of the flip flop. The condition that S and R is equal to 1, which was not permitted in the previous case, how that is eliminated in this case of JK flip flop we will see. For that we need to make S is equal to 1 and R is equal to 1. Of course, we will analyze the circuit when clock is 1, because when clock is 0, flip flop is not going to be input is not going to be effective. In this sense, the flip flop is going to store whatever value was put in it before the clock became 0. So that means we are going to analyze the condition 1 1 for these two inputs, 1 1 for these inputs. So let us assume a condition of the output being 1, because we have to start somewhere, Qn 1 and Qn bar 1 0, and when, since we have fed back this Qn and Qn bar, so this is going to become a 0, this is going to become a 1. So this is a 1 1 1, output is 0, 3 input NAND gate, 0 1 1, output is a 1 for a 3 input NAND gate. So this condition is going to be the condition by which, because of the inverse of the NAND gate, this becomes a reset condition. Earlier we saw this 2 input NOR gate connected back to back as a RS flip flop. Remember that? RS latch. That means R is equal to 1, S is equal to 0, made a reset condition. That means it is going to become 0 output and 1 output. So we have now made use of a condition of 1 1 from an unstable condition, not, I won't say unstable, unpredictable condition, a condition which cannot be the 1 1 input in a SR flip flop was not used, because what happens further to that input is not clearly defined. That has been eliminated. Now 1 1 is the input, will give you a change from 1 1 to 1 0 to 0 1. 1 1 would have, earlier it was 1 0, convert to 0 1. This condition is called toggling. Toggle stands for change of the output from 1 to 0 or 0 to 1, toggle. But unfortunately this is not going to be all that simple, because the clock continues to be 1, input continues to be 1, yes, input continues to be 1, but now we have changed output from 1 0 to 0 1. Remember, there is a feedback. So this feedback gets this 1 back into this, and this feedback gets this 0 back into this. So now instead of inputs being 1 0, because it's a 1 1 1, this input becomes 0, this becomes 1, and there is a reversal of the condition. Earlier it was a 1 0, which resulted in a 0 1 and a reset condition. Now the 0 1 is the input, the RS latch gives you a 1 0 or a set condition. So this keeps going, this keeps going. That means as long as the clock is high and S is equal to 1, R is equal to 1, these inputs keep feeding back, outputs keep feeding back to the input, the output keeps toggling. This is not what we want. We want an RS condition where both are 1 and defined useful output. A defined useful output is alright, that in the sense that it toggles. It means whatever is the original output. So if you write the truth table, I am going to introduce for the first time letters J and K. The 3 input NAND gate expanded version of the SR flip flop, now called a JK flip flop. We will call this JK instead of SR. JK flip flop works like a SR flip flop for the 3 input 0 0, 0 1, 1 0, but for the condition 1 1 which was not permitted in the SR flip flop, we have now established that the output changes. If the output was 0 here and a 1 here, it will become 1 here and 0 here, or the output was a 1 here and a 0 here, it will become 0 here and 1 here. That means output toggles for the condition of 1 1. So we will call it Qn bar. That means whatever was Qn, the complement will be the output. So this condition is what I said is the toggle condition. Toggle condition is all right. So this is a memory condition. This is a reset condition, so set condition. Toggle condition is a desirable condition as against as Rs is equal to 1, R is equal to S is equal to 1, not permitted in the case of SR flip flop. But the desirability does not stop there, because the constant feedback of Qn and Qn bar back into the input NAND gates keep toggling the outputs as long as the clock is high. When the clock becomes 0, then the activity stops, because once the clock is 0, the output gets defined. Once one of the inputs is 0, this becomes 1, and then 1 1. When it is a 1 1 output corresponding to the RS flip flop is 1 1, which means the memory condition will return. Now, in order to, this condition is called the raising condition. Constant changing or toggling of the output of the JK flip flop or any flip flop for that matter, as long as the input is clock is high, as long as the clock is high, if the output keeps toggling all the time. And what is the time of toggle? The time of the toggle is decided by the propagation delay of the gates. So, how much time does it take for the input to propagate from here to here to here and back here? That is the toggle time. At the end of this period, it go back. So, this toggle time is determined by the delay of the two gates. It will be very, very small, especially the modern day gates, the delays are very small and nanosecond of that order, whereas we can never have a clock of width less than that. If we had a clock width less than the propagation delay of this flip flop, then toggle will not happen, because supposing by the time I change my input from the input, and then by the time the input reaches the output and changes the output, if I remove the clock, then toggle will not happen. Toggle condition requires clock to be high. So, if you put a clock high, put a set of inputs and let the output change, and by the time the outputs propagate back into the input, if the clock is already removed, toggling cannot happen. That means I need to operate with a very, very, very high clock, which is not possible, which is not also required. So, I should have some other way of controlling the toggle. That means I need this desirable condition of 1 1 as a toggle condition, which is an improvement from a SR flip flop. On the other hand, I do not like this raising, where the output keeps changing. The only way to avoid it is to make a clock which is very, very small in the width. Clock frequency should be extremely high, which is also not required. Why should I operate my flip flop at that rate? So, what are the other ways in which I can change the or remove this raising condition? There are two simple ways. Again, it is a review, so you should have heard about these things earlier. One is called the master slave operation. I will not go into the details of this. In a master slave operation, what happens is we have two flip flops, identical flip flops, JK, SR, whatever you want to call it. Q, only difference is I will feed this flip flop with a clock and this with a clock which is inverted from this clock. It means the clocks are inverted. One of the clock when it is positive, one of the clocks is positive, the other clock is negative, and vice versa. I mean positive negative, I mean 1 and 0. So, when the clock is 1 here, 0 here, or high here, low here, low here, high here. That means even though the input can change and toggle, we cannot get this input passed on to this. So, where the toggling is because of this overall inside. I don't have the access to the, I don't have the access to these inputs. The feedback is overall. This input gets feedback from here, and this input gets feedback from here. The input, 3 input NAND gate of this J, 3 input NAND gate of this K are getting feedback output from this Q and this Q bar. So, even though I have put a clock on the JK condition 1 1, output changes, but this flip flop will not take it through because the clock is low. So, even though there is a feedback, the feedback will not change as long as the clock is low. Moment the clock is high, this feedback condition will reach here, the change in condition will, the output will change. The output, by the time the output changes here, since the clock is, when the clock is high here, the clock will be low here, the clock will be removed. So, I can operate at any desired clock rate because this flip flop and this flip flop are isolated, these two flip flops are isolated in their operation. When this is effective, this is not effective, when this is this is effective, this is not effective. So, I am practically taking 2 steps. Any change in the input will change the output as long as this clock is high. At that time, this flip flop will not have any change in the output because the clock is here low. When the clock is low, the flip flop output does not change. When the clock positive period is over, when the clock high period is over for this flip flop, that will be put here. This flip flop becomes clock high. Any output at that time will be the input to the flip flop, and that will change. But no more change is possible in this flip flop because the clock has already been removed. This way we can eliminate the racing condition. It is called master slave operation. Requires an extra hardware, of course, an additional hardware. Extra thing you need to do means you have to pay something, and that payment comes in terms of an extra flip flop. That way I don't have to worry about my clock width having to be very, very narrow in order to avoid the racing as is required in a non-master slave. But one objection to this would be we have to use 2 hard blocks to get the same operation. 2 flip flops are required in order to get a master slave operation. That is one problem. The second problem would be the overall, supposing I want to go in a mode where I will have very high operation of the clock, because this is a very extremely unlikely case today's technology. Today's technology we are talking about gates of nanosecond or sub nanosecond delays. So, when the delay of a gate is less than 1 nanosecond and a couple of gates in the path of this and a couple of gates in the path of this, a total of about 4 or 5 gates, 4 or 5 nanoseconds corresponds to very high clock rates. 10 nanosecond corresponds to 100 megahertz, 4 or 5 nanosecond corresponds to let us say 5 nanosecond will correspond to 20 megahertz, 200 megahertz operation. Very unlikely, except that then we are talking of today's technology, Pentium 3, Pentium 4 processor, we talk about gigahertz operation. Whatever it is, I don't want to question your need. Supposing you want to operate at a clock rate which is faster than the propagation delays which 2 flip flops can allow you to do, that means why should I be restricted by the speed, why should I be restricted in the speed of operation by having to pass through 2 flip flop hardware. That means why should I unnecessarily increase the propagation delay of the path if it is not required, plus the fact that there is extra hardware required. That makes you think whether it is the best solution. Of course, there is one solution, as I said, the other solution is edge triggering. This also is familiar with, you are familiar with. Edge trigger flip flops. There is another way of removing this. This is same as the condition. I do not want the change in the input to propagate more than once during a clock period. That is the basic theory. That we did here by preventing the clock to the second flip flop. One other way of doing it is I will let any change in the input change the output only when the clock changes from 0 to 1 or 1 to 0. In between, even though the clock is high, any change in input will not affect the output. This is called the triggering operation, edge triggering operation. That means what I am trying to say is, if this is my clock, and this is my input, D input, let us say, it's a simple D flip flop I am talking about. Let us say this is my D input, let us say this is my Q, output of the D flip flop. It's a simple D flip flop. Let us say only when the positive clock edge or the positive transition of the clock from 0 to 1 any change in the output will happen based on the input. Output of the flip flop will change based on the input, that is sure. But when will it happen? Only when the clock transition occurs from 0 to 1. Rest of the time, even though the input may change, the clock, the flip flop will not recognize the change in input. It will recognize the change in input of the flip flop only when the clock transition occurs from 0 to 1. This is called positive edge triggering. Positive. Why positive? Because it is going from 0 to 1. Clock edge going from 0 to 1 is called positive edge. So now let us assume the flip flop output was a 0. Even though at this point what will happen, it will look at every transition of the clock, the flip flop circuit will look at the input continues to be 0. So nothing happens. So the D input has changed from 0 to 1 at this point. Will this affect the output? No, it will not, because it is not occurring at the positive edge. It has already passed, the positive edge has already passed before D became 1. This change has to wait for the next positive edge. Until this positive edge, which is the second positive edge, this input in D will not be recognized. At this point in time, again the flip flop input will be looked at, which is D is equal to 1, and when D is equal to 1, the output will be Q is equal to 1 for a D flip flop. So this will become 1. Having this Q has become 1 from 0. As soon as this edge disappears, a little time afterwards, D disappears, D becomes 0, but it is not going to affect the output because output has already become 1. It will not be looked at all here, it will be looked at only when the third positive edge occurs, and that will happen. When that happens, it will look at D again, D is 0, output will go back to 0. This is called positive edge operation. This is one way of preventing raising. Supposing I make a flip flop, whatever is the hardware or logic inside, my inputs will be recognized or looked at only during the clock transitions, either from 0 to 1, in this case it is called positive edge triggered, or from 1 to 0, in which case it will be called a negative edge triggered. Only at that time alone, only at that time outputs will change, and rest of the time the output will not change. That way I can eliminate the possibility of a raising, and I do not have to worry about 2 flip flops having to be put in the circuit, and this can occur at any speed. Speed of operation is not a limitation in this case because I am going to have a single flip flop. Of course, the speed of limitation still depends on the propagation delay of the flip flop, because there has to be a hardware for any flip flop, there are a couple of gates and some other extra logic, we will talk about it a little later on. Some extra logic is also required. So there is going to be propagation delay, at least I do not have to double it. Here I am purposely I am doubling it. Doubling the propagation delay I am avoiding, that is all. That does not mean that propagation delay is 0. No hardware can have propagation delay 0. There will be propagation delay, but that will be the only limitation of my speed, and I have also filtered the possibility of output changing any time. It will happen only when the clock changes. It is called positive edge trigger. Similarly, you can draw a waveform and for negative edge trigger. I am not going to talk about it here. You can also think of a negative edge trigger. So, these are the two options, the master slave option where you require an extra flip flop, because of that the extra hardware and the little slowing down of the maximum frequency of operation. I will not worry about it too much. The maximum frequency of operation today is so high, and most of the common circuits that we design in digital circuits, except in very high performance circuits, this is not a problem. The other hand, we have a edge triggered operation where we will allow the output to change only input based on the input only once in a clock period. It can be at the positive edge of the clock or the negative edge of the clock. In one case it is called positive edge triggered flip flop, other case is called negative edge triggered flip flop. And when doing so, we will still have to worry about the speed of operation by decided with the propagation delay, but we do not have to worry about the toggling condition and all that racing condition. We said that the edge of the clock determines the operation. Only during the clock edge any input will be recognized. It is easy to say, but how do you implement it? Because when you are going to have a flip flop of JK type here, we have inputs occurring and the clock occurring, and you cannot suddenly remove one of them and say it is only for a short duration. So, the actual way in which it is done is put an extra circuitry at the input of each of these flip flops. Each flip flop input, that means if it is a JK flip flop, 2 inputs, for each of these inputs you need to put this extra circuitry. So, there will be an extra circuitry that has to be put at the input of each of these. Let us just understand this circuit. This is one of the possibilities. This is not the only way in which you do the edge triggering. This is one possibility. Let us independently consider, without flip flops or latches or RS or JK, we will independently consider this circuit. It is a simple gate, NAND gate and OR gate. This NAND gate has 2 inputs A and B, output is C. The C is one of the inputs of the OR gate, the other input of the OR gate is same as the B. So, D is C is A and B whole bar, D is C or B. Now, let us assume randomly or arbitrarily, not randomly, arbitrarily an input A, which this is the time axis, x axis is the time axis for all the waveforms. Input goes from 0 to 1 somewhere here and keeps as 1. B waveform remains 0, remains 1 for a while, goes to 0 for a fixed duration, goes back to 1, comes back to 0 for a fixed duration, so on. Now, the output of C, the output C is the output of the NAND gates when A and B are the inputs, is given by this. C would be 1 when this is 1, when both are 1 this C will be 0, when both inputs are 1, that is going to last for this duration. Again, since one of them is going to become 1 and one of them is going to become 0, this is going to become 1. Again 1-1 combination results in 0 for this duration, back to 1 because this will become 0 and so forth, it continues. This is output at C based on the simple NAND gate operation. Now, I am giving D as the input to the D as the output C and B, I mean output C or B actually, what I meant was output C and B are the 2 inputs to the OR gate D. So, we have this D would be based on B and C. Now, we will see that all the time I am looking at these white lines, not these yellow lines which I have drawn later on, which will be explained little bit later on. This is 1, this is always 1, and when this becomes 0 this is still 1, when this becomes 0 this is 1. So, either of B or C is always 1, which means C D will be 1 continuously. Why I am explaining this I will tell you in a minute, but this is an ideal operation, no gate is ideal. What will happen is each of these gates C and D has a propagation delay. Let us assume a small delay of this duration. Even though A and B are applied, A has been continuously there, so there is no question of it is changing. So, B changes from 0 to 1 and 1 to 0, etc. C will not immediately, even there is an input change condition. As far as C is concerned, there is a condition of the inputs from A is equal to 0 and B is equal to 1 to A is equal to 1 and B is equal to 1. That change will not immediately reflect the C output, it will reflect after a short time. That is why we use this colored chalk here, yellow. The short duration is because of the propagation delay of the gate C. Likewise, when it goes back from 0 to 1, this same propagation delay will act. So, the propagation delay of C gate 1 will shift the output C from the original point here and here to this point and this point. So, the actual output would be, practical output would be this yellow line for each cycle. Again there is a change here, so this will not come here as depicted earlier, but will come a little later and again go back to 0 a little later. So, the yellow line is a modified output line at C because of the propagation delay of gate 1. Now, making these OR gates, inputs as this and this, the new line yellow, there will be a short durations during which there will be both zeros. For example, this duration here is the duration to which this is 0, B is 0 and C is 0. B and C are both 0 here, so the output has to be 0. Originally we said D was 1 continuously. Now I am saying because of the propagation delay, this is 0. Again this 0 will not occur here, it will occur a little shifted. So, if you want to be perfect about it, I cannot use, maybe I can use another colored chalk, and this will really not happen here, it will really happen a little bit. All these exaggerated drawings just to make it clear to you. So, this should be the green line, if you call this green, some sort of a light green. This is where output of D. Earlier the output was always 0, now I have a short duration for which it is a earlier D was constantly 1, now I have a short duration for which output is 0. That is going to occur again here, and again when this goes back to 1, like that. Now, if I want to give as this D as input a flip flop, the flip flop input remains 0 for a short duration of time. Now, you can have this A can be the input, for example, for the flip flop, D flip flop maybe, B could be the clock cycle, and every time that the clock goes from 1 to 0, it is negative edge. Every time the clock goes from 1 to 0, correspondingly there is a output pulse based on this input. Of course, it so happens it is a negative. I want a D input. If this is a D and this is the input will be applied. So, clock is high, even though the clock is high, the D does not remain 1 all the time. Of course, D is 0 in this case, I will have to do some inversion, one of these gates has been inverted, this is only a concept. So, I have to invert one of these gates, maybe this NAND gate can be an AND gate. If you make one of these inversion, this becomes a positive pulse instead of negative pulse. So, what I want is corresponding to the input which is constantly 1, I want the input to be a narrow pulses every time the clock changes. Every time the clock changes, in this case from positive to negative, that means negative edge. Every negative edge the output becomes a small pulse. So, now I can change this into a positive pulse by, as I said, changing the configuration of the gates. I can make it this pulse into the positive edge triggered by again making some changes in the circuit. Changes in the circuit can lead to a positive pulse and at the positive edge trigger. So, I can have a positive pulse at positive edge, negative pulse at positive edge, negative pulse at negative edge, negative pulse at positive edge, whatever is the combination I want by different types of gates. We have NAND gates, NOR gates, AND gates, OR gates. By combination of these gates, the idea is to use the delay of a gate, that is all there is to it, nothing else. The delay of a gate is used in order to make the input, even though it is always available at the input of the flip flop, when it actually reaches the flip flop gates, the NOR gates, which does the flopping operation. The flip flop operation is because of the, remember that RS latch we started with, the 2 NOR gate inverted, that should be the one to which the input is considered. All other things are only external peripheral circuitry. So, to that input circuit, the input will change only very narrowly like this. So, this is how an edge triggered operation comes. Now, in edge triggered flip flop, what happens basically is then, edge triggered operation what happens basically is then, at each input of the flip flop, here we said simply the JK flip flop has the master slave flip flop has 2 identical flip flops. But in the edge triggered flip flop, I said simply, it is very easy to say that there is only one flip flop, so I reduce the hardware. The speed of course is the speed of the propagation, I said. Now, that is not all quite true. I need to add the input to the input of each of the edge triggered flip flop, whether it is a JK flip flop, SR flip flop or a D flip flop. Whatever is the edge triggered flip flop I am constructing, to each of the inputs of a flip flop other than the gate, other than the clock input, I need to add a little edge triggering circuitry. This circuitry shapes the input into narrow pulses which will only be applied to the flip flop, and only at that condition the output will change. Rest of the time the output will not change because the input is removed after that narrow pulse period. This is how an edge triggered operation works, and this becomes an input to the sort of a pre-processing, if you want to call it, a pre-processing circuit to each of the inputs of any flip flop, if you have to have it as an edge triggered flip flop operation. We will stop here for today.